It couldn't be any thriving modern country town
Anywhere in Australia. Attractively laid out, plenty of parks and gardens, offering shelter from the blazing sun, up-to-date shopping facilities, and all the other amenities that help to make up the good life. But this is a town with a difference. Mount Isa in northwestern Queensland, 1,600 kilometres from Brisbane and 1,000 inland from Townsville. Mount Isa's prosperity results from its status as the world's biggest single source of lead, second in silver, and among the top 10 in copper and zinc. Less than a kilometre from the town, other mine and treatment works with smokestacks in the past have been responsible for one of Mount Isa's major problems, pollution. For most of the year, the town is protected by a prevailing southeasterly wind, but sometimes in the summer, a sudden change to the west can blow stack gases back over the city, raising sulfur dioxide concentrates to unacceptably high levels. As part of an environmental protection campaign costing over $20 million, ranging from water quality control to computerized monitoring of weather conditions and gas flows, Mount Isa Mines Limited decided on a dramatic step to help clean up the local air. Toward the end of 1976, technical experts of Mount Isa Mines and the Melbourne-based construction company Talman Australasia conferred on a plan to reduce and hopefully remove a major source of pollution from the lead smelter. The scheme involved building a new stack for the smelter 270 metres high, which Talman undertook to design and construct. From such a height, it was calculated, the sulfur dioxide fumes would be dispersed harmlessly into the atmosphere under almost all atmospheric conditions. This major project, the biggest of its kind ever attempted in Australia, presented a number of unique problems. At Monash University, scientists subjected a scale model of the stack to wind tunnel tests, simulating the known velocity of extreme wind gusts at Mount Isa. The degree of deflection of the stack when exposed to such gusts was observed and recorded, from which it was possible to calculate the stress it would suffer under typical wind conditions in Mount Isa, and consequently to determine the nature and design of the structure itself. Within 3 months, Talman and MIM engineers produced a complete design and work program for the whole project. Construction work on the new stack began at Mount Isa in June 1977, after lengthy testing of the load-bearing capacity of the selected site, adjacent to the existing stack. Considerable levelling and removal of topsoil were necessary to prepare a proper foundation on bedrock before construction could actually commence. Large quantities of lead were used in tests which measured the load-carrying capacity of the bedrock. The structure was built on a ring-like footing 28 metres in diameter and 3.5 metres thick. The ground on which it rested proved to have a high bearing capacity, but also to contain a number of voids, which were filled by means of a special non-shrink grout. Once the grouting was completed in mid-August, work began on the pouring of an enormous footing. This in itself required some 1,600 cubic metres of concrete. Work proceeded on the job around the clock, 7 days a week. Talman's schedule provided for the giant stack to be completed within 18 months of commencement, to coincide with the construction of lead smelter modifications and a planned production shutdown to bring them into operation. Coordination of the two projects depended on keeping to a rigid timetable. Each new stage had to be ready to go into operation as soon as the previous one had been completed, to prevent any possible delays. With the foundations finished, the complex slip-forming equipment and working platforms for the stack itself were erected after 6 weeks' intensive activity. Work on the stack then began. The slip-form technique used in the construction of the outer windshield entailed raising the level fractionally as work progressed by means of hydraulic jacks. This is now fairly standard procedure for vertical structures of constant wall thickness, but becomes extremely complicated if the walls are inclined inwards and varying in thickness. 120 jacks spread around the interior of the windshield in groups of 3s were operated to raise its level 25 millimeters at a time. In this way, the height of the structure rose by as much as 6.5 meters in a full day. The reduction in diameter and wall thickness was achieved by 40 sets of manually adjusted screw units. This was the first time the method had been used under such conditions in Australia. Talman's design for the windshield called for a reinforced concrete structure tapering from some 22 meters diameter at the base to just over 12 meters at the top of its 265 meters height. Wall thickness varied from 700 millimeters to 235 millimeters. The windshield alone required another 4,500 cubic meters of concrete, as well as 450 tons of steel reinforcement. Even the concrete caused problems due to the difficulties of the job and the severity of Mount Isa's climate. With the mercury often topping 40 degrees centigrade, ice was mixed with the materials to control its temperature and ensure that it's set to suit the construction requirements. As the windshield crept upwards towards the 76-meter level of the old stack beside it, new problems had to be solved. Wind tunnel tests had shown that the existing stack would be severely affected by the new structure. From certain directions, wind forces would be greatly magnified, causing overstressing and conceivably even the collapse of the old stack. Temporary steel guys were installed to buttress the stack, attached either at ground level or to the sides of the new windshield. Gases from both the lead and copper smelters presented a potential danger to the construction workers. It was therefore necessary to enclose the entire working area to keep out noxious gases from the other stacks nearby. A novel solution was devised by erecting a protective cocoon around the working platform, consisting of polystyrene panels 15 meters high with a skin of aluminium each side. The cocoon was sealed to the windshield by rubber flaps, and the whole interior of the windshield pressurized by a large axial flow fan at ground level, which kept clean air circulating inside and was strong enough to prevent any fumes entering except at very high wind conditions. With the cocoon completed, the windshield began to rise above the old lead smelter stack beside it. As the structure climbed higher, concrete was delivered to the working platform inside the cocoon on giant hoppers, hauled up by lift from the base of the stack. Extensive backup and monitoring equipment was employed to measure and predict wind speeds which may have affected the stack. Gas masks and other breathing apparatus were provided for every worker on the deck in case of emergency, but never had to be used. Thorough safety precautions of all kinds ensured that not one major accident occurred during the whole construction period, despite the intensive program involving continuous shift work. Horizontal levels were constantly checked, while verticality was controlled by means of a laser instrument. And the tilt of the working deck was adjusted to steer the framework into its correct position. A considerable amount of reinforcing was necessary to counteract the process of ovalization, as it's called, the bending movements produced in a horizontal section due to variations in wind pressure around it. During the day, as various parts of the windshield were exposed to the direct rays of the sun, the structure bent due to uneven thermal expansion, which required careful control. With the windshield reaching its final height of 265 meters in March 1978, after only 3 months construction, work then began on the installation of the inside flue liner. Made by Rheem Australia Proprietary Limited at its Townsville plant, the flue was transported 1,000 kilometers overland from the coast on outside carriers in 10 can-like sections of approximately 27 meters in length, weighing about 35 tons each. The 4.4 meter flue was fabricated from structural grade steel varying in thickness from 6 millimeters to 10 millimeters, covered by a 50 millimeter insulating shield of fiberglass. The inside had already been treated with a special tar epoxy paint. Before erection, the 5-meter section, which would protrude from the top of the stack, was wrapped in protective strips of stainless steel. Erection of the flue was a feat in itself. The separate sections were maneuvered into the base of the stack, where they were hauled up one by one by a system of center-hole hydraulic jacks, similar to those used in the slipform operation. 6 internal platforms were installed inside the stack from the top down. The top platform was designed to take the full 350-ton weight of the assembled liner. As each section was raised vertical and hauled up the stack, the next was positioned underneath it, and the two then field welded together. The 2 cans were then raised a further distance, and the process repeated until the complete liner was assembled and hanging from the jacks and their cables. This is now a fairly standard operation, but was complicated in this case by the length of the cans and the difficulty of inserting them into the windshield and suspending them vertically before they could be raised. As the installation of the flue was nearing completion, the protective cocoon in which the men had worked for nearly 9 months was dismantled and lowered to the ground, panel by panel. Perched on the very top of the nearly completed structure, 265 meters above Mount Isa, the men were safe from any effects from the gases of the old lead and copper stacks below them. But the removal of the final stages of the cocoon and its scaffolding was a hazardous operation. All that remained now was for the top of the stack to receive a protective coat of paint. The inside of the windshield is large enough to accommodate another flue in the future. Around its walls are 6 platforms designed to permit ready access for maintenance, as well as servicing the aircraft warning lights on the outside. All platforms are provided with adequate lighting, together with a wide variety of other power supply sources for maintenance and inspection. The monitoring of gas flows is carried out through a series of flanged openings at the 45 and 90 meter levels, and the information obtained used for plant performance predictions, as well as providing environmental data. Access to the platforms is by a rack and pinion hoist, capable of carrying both passengers and equipment, backed up by an emergency ladder running parallel to it. Finally, right on schedule in November 1978, only 23 months after Tileman's technicians had begun their feasibility study of the project, and 16 months after construction had commenced, word was given for the giant stack to be switched in to the production system. High above Mount Isa, the sulfur dioxide effluent floats away from the giant stack, which forms an important part of a major program to improve the quality of life for Mount Isa's residents and the quality of the air they breathe.